All right, so this is a review of homework 4, which is an introduction to conditional introduction, which is one of our two hypothetical rules that we use in natural deduction. The other hypothetical rule we'll be covering in the next homework, and that the rule of negation introduction. So as always, I'm going to assume some familiarity with the rule and how to use it, but I'll just briefly summarize here. So conditional introduction is a rule that we use whenever we need to, or at least one that we have access to, and which will often help us to prove any formula that has a conditional nature. So basically anything that has the form if A then B, where A and B of course can be any formulas at all. And it doesn't just have to have the form if A then B, it could just be logically equivalent to that form. So the fundamental idea behind conditional introduction is if you want to demonstrate that if A then B, what you can do is hypothesize A, take A on as a temporary assumption, and then attempt to derive B. And if you do hypothesize A and successfully derive B, then the rule of conditional introduction says that you can now assert that if A then B. So the idea of a hypothesis here is extremely important. It means you're not assuming it to be true in the way that you assume the assumptions. You are just taking it on for the purpose of deriving this conditional and then actually discharging that hypothesis. So a really simple example of how this method works would be to consider this argument, if P then Q, if Q then R, therefore if P then R. Now, you can see on inspection that this is a valid argument. In fact, it's a rule called hypothetical syllogism. But if I asked you to prove this just using our 8 basic inference rules, you would be unsuccessful. We don't have the power to prove this yet. So we introduce the rule of conditional introduction, and it works like this. We take on if P then Q as an assumption. We take on if Q then R as an assumption, and then we say, well, suppose we hypothesize, which we represent by an H, and we also indent very significantly so that we can see that it's been indented. We hypothesize P. And then we say, what happens if we hypothesize P? Well, if we hypothesize P, then it's going to follow that Q, notice that Q remains indented by 1, 3 conditional elimination. And now that we have Q, we can also have R remaining indented by 2, 4 conditional elimination. And then we say, oh, look, we have now derived R. So we are in a position to say that if we hypothesize P, then we can get R. And so what we do is we just assert that. And the rule tells us that the way that we assert that is to remove the indent and write if P then R. So notice what we're doing is we're writing if the hypothesis, then the very last thing we derived. Okay? When we do that, we drop a line right here. And what this line tells us is that everything on the right side of it was just part of a hypothesis. It's essentially a fantasy world where all we did was derive a conditional. So nothing we wrote after we hypothesized P are things that we've proved to be the case. They're only things that follow if we allow ourselves the hypothesis, and that's all we are asserting when we assert if P then R. So many people on first reading about this think that there's some kind of magic associated with this and that we're cheating in some way, but we're not, because we're not asserting that R is the case. We're just asserting that if we're allowed to hypothesize P, then R follows. And the way that we justify this is we say 3 through 5. So 3 through 5, conditional introduction. Okay? So it's very important to understand that once we discharge the hypothesis, everything on the right side of this line is no longer in service. If there were anything else to do in this proof, and that will often be the case as we'll see later, you would not be permitted to go back and use anything on the other side of this line. It's been discharged from the proof itself. The only thing you're allowed to use is the conditional you've derived. All right, one more quick example, maybe another couple quick examples. We can actually use conditional introduction to prove what we call theorems. And theorems are essentially the proof theoretic versions of what in the semantics we call tautologies. And ideally, anything that we ever assert as a theorem or are able to prove as a theorem in our proof apparatus should also be a tautology in our semantic apparatus. So a theorem is something that you can prove through no assumptions whatsoever. Okay? So the idea of a proof with no assumptions might seem odd to you, but that's exactly what a theorem is. Okay, so here is a nice little theorem. If P, then if Q, then P. So what this is essentially saying is that if you know that P, then you know that if anything else, then P. So how could you prove this? Again, like I said, from no assumptions. What you would do is you would start out immediately with the hypothesis. So you say, okay, that's the main operator. So I'm going to start out by indenting, right? Make sure it's clear that you're indenting. And you call that a hypothesis. And then you say, okay, what am I trying to do? Well, I'm trying to derive if Q, then P. Now what you notice is this too is a conditional. So you hypothesize a second time. And so you indent even further. Okay? So you hypothesize P and then you hypothesize Q. And now all you're trying to do is derive P. Well, you're in kind of a funny situation here because you've already got P in the hypothesis, so you should be able to do this, but you don't have a rule that just allows you to rewrite P. We will eventually have that rule. It's called the rule of reiteration, but we don't have it now. So what we have to do is get creative, and what you do here is you use conjunction introduction, right? So you can write P and Q by 1, 2, conjunction introduction. And actually, the truth is that you could have even written P and P, because the rule of conjunction introduction does not require you to use two different lines. It would be natural to assume that, but it doesn't say that. So you could write P and P and with one and introduction if you wanted to. But either way, now you have P and Q, and so now you can write P by 3 and conjunction elimination. If this seems artificial or dumb to you, I understand that, but that's just the way that things go sometimes. Sometimes you have to just come up with clever little tricks that allow you to do things that you really feel should be able to be done much more easily, but which your rules don't yet permit you to do easily. Okay, so now what do? Well, we've just shown if Q then P. So now we can discharge the second hypothesis by writing if Q then P. And we always have to discharge in reverse order. Okay, so we discharge the last hypothesis first. So now we have Q, if Q then P by 2 through 4, conditional introduction. And then now we notice that our proof actually says if P, then if Q, then P. So now we can assert that, right? Notice how it's working. Here it is, hypothesis P, the last thing we proved, if Q, then P. So if P, then if Q, then P, drop the line right there. And now we assert 1 through 5 conditional introduction. It's a little awkward that it says 1 through 5 because that actually suggests that we are using 2, 3, and 4 in the derivation, which we've already discharged, and so we said we're not allowed to use that. It does not mean that we're using that. You just sort of have to get used to that kind of awkwardness. It just that we used everything between 1 and 5 except things that are no longer available. Okay, so that's how a theorem can work, how we can actually prove something from no assumptions, which was not possible for us before the rule of conditional introduction. And let's just take a look at one last example. Suppose we were asked to try to show that from P and Q, it follows that P, if and only if Q. Now that is not intuitively obvious. You might say, look, just because we have P and Q, it certainly doesn't follow that there's some sort of important relationship between them. And that's a strong intuition for life, but it just doesn't tend to hold up in logic because of the nature of the material conditional. So here what we'll do is we'll take on P and Q, which is given to us as an assumption. And now what we say is, oh, we're trying to prove a biconditional, but you know that a biconditional is just a conditional that goes both ways. So what you want to do is say, first I'll prove if P then Q, then I'll prove if Q then P, and then I'll just put them together at the end using biconditional introduction. Okay, so this feels a little peculiar because why would you hypothesize P when it's already in an assumption? But the answer is because you want to show if P then Q, okay? And the only way you can do that is by hypothesizing P. At least that's the only way you can do it now. So even though you have P in an assumption, you're going to hypothesize it. And then all you have to do is assert Q by and elimination. So one conjunction elimination, and voila, you have shown if P, then Q by 2 through 3 conditional introduction. Okay? So you have the first one, if P, then Q, and then you just have to go the other way. So now you're going to hypothesize Q, right? So notice before we had what we call nested conditionals, where one is done in the context of another, and here we have sequential conditionals where one is coming after the other. So hypothesize Q, and then we just do the same thing. We do P by 1 and conjunction elimination. Notice that we didn't do that P, right? Because that is no longer available to us. Okay, and then we assert if Q, then P, drop a line, 5 through 6, conditional introduction. And now we've shown if P, then Q, and if Q, then P. So we could write if P, if and only if Q. Notice we're completely out of the indentation now, so we have this free and clear. I could also have written Q if and only if P if I wanted to, but that's not what I want, right? So we have P if and only if Q, and that's just by 4, 7 by conditional introduction, okay? So that's how conditional introduction works. So let's go ahead and just do some of these homework problems. So the first one gives us 3 assumptions, P and Q, a conditional, if Q, then if S, then T, and another conditional, if P, then if T, then R. And if you reverse engineer this a little bit, right, you'll say, look, I'm trying to prove a conditional. That probably means I need to hypothesize S. But before you do that, you might look at the assumptions and see if there's any value you can get by just breaking things down a little bit more. So you see that you have P and Q, right? Which means that you could have P and you can also have Q by and or conjunction elimination. Q will give you if S, then T. P will give you if T, then R, right? So you could get some value by doing conditional elimination on the first assumption and then applying each of these conjuncts to the conditionals. So then you would have if S, then T on a line, and you'd have if T, then R on a line. And then you just have a version of a proof we just did, the hypothetical syllogism proof, right? So you just hypothesize S, and you would get R by 2 applications of conditional elimination. Okay, so the first few inferences are going to look like this, or at least they could look like this. Suppose because you were very anxious to get started on a conditional introduction, you just immediately hypothesized S. That's okay, and you're going to get it done. The only drawback to doing that is that now anything that occurs under this hypothesis is not going to be available later if you discharge the hypothesis. So the advantage of doing any obvious inferences before you do the hypothesis is that you have them available for later use. Again, all that does is save time. It's not, or save space. It's more an aesthetic issue than a logical one. So let's just go with sort of rookie intuitions here and hypothesize S to make sure you see that it would certainly work. And what would you do after that? Well, then you would do what we said before. You would start breaking down P and Q and making the obvious inferences. So suppose you went ahead and say only got P by 1 and elimination, and then you immediately went and got if T, then R, right, by 3, 5, conditional elimination. So then you can do the same thing with Q. Go back and get Q by 1 and add elimination, and then just repeat that process with Q. So you generate if S then T by conditional elimination. And then feed your hypothesis into if S then and get T by conditional elimination. Okay, so just to emphasize, this is just one of several sequences you could have done in order to generate this result, but the important thing is that you've got T, and then from T, right, now that you have T, you can feed it into 6 to get if T then, feed it into 6, which is if T then R, in order to get R by 6 through 9 conditional elimination. And there you've achieved your goal, right? You've hypothesized S, and you have derived R. Notice that you've been indented the whole time, right? So now you're going to take away that indent by discharging, right? You've got if S then R, so you drop a line right here. And now you are allowed to assert if S then R by 4 through 10 conditional introduction. Okay? So that's all there is to that proof. Okay, number 2 actually bears some resemblances to the theorem that we proved above. We're supposed to prove, this is not a theorem because we're given an assumption, but we're supposed to prove from if Q then R and S that if P then if Q then R. Okay, so this is 2 conditionals in a row. The first one is the main operator, but then we're left with conditional to prove. So we're going to go ahead and hypothesize P, right? But after that, we're going to hypothesize Q, right? So having hypothesized P, our goal becomes to show if Q then R. But since we're supposed to show if Q then R now, we'll hypothesize Q, and this reduces our goal just to demonstrating R. It's important to be thinking in exactly this way. Successive hypotheses should be made whenever possible because they simplify what it is that you're trying to prove. Okay? So when we hypothesize P, right, I remind myself here on the side, that means that we're trying to get if Q then R. When we hypothesize Q, that means now all we're trying to do is get R. But that, of course, is a very simple task because now that we have Q, we have if we have R and S by conditional elimination, right, then all we have to do is apply conjunction elimination to get R, and then we just discharge our hypotheses from there. Okay, so R and S by conditional elimination, R by conjunction elimination. Now we have if Q then R, which we can assert by dropping a line right here, right? And asserting if Q then R by 3 through 5, conditional introduction. But now we can see that we've actually got if P, then if Q then R. So now all we have to do is drop another line and assert if P, then if Q then R by 2 through 6, conditional introduction. Okay, number 3 is a funny little proof, and we can learn some things by doing it. It tells us that we should be able to show that if it's the case that R or R, then it follows that R. And if you think about it semantically, you know we should be able to prove this because the only way that R or R could be true is if either R is true or R is true, right? So either way, it should follow that R. I know it sounds funny to talk that way, but that's what the formalism is telling us, okay? So here you might be saying, well, okay, I get that we should be able to prove that, but we don't have any conditionals here, so I don't even see why this problem is on this problem set. But then you're going to remember something, hopefully, and that is that we have a rule called disjunction elimination, and disjunction elimination involves 3 lines. It involves the original assumption and 2 conditionals, okay? Now the difference between this homework and the last one is that now we have the basis for deriving these conditionals by conditional introduction. So here's 2 very important things. One is that sometimes we use conditional introduction to prove a conditional that isn't our main conclusion, but some subsidiary conclusion that we need to get to our main conclusion. And that is very often going to involve the use of disjunction elimination. So what is it that we need to prove here? Well, disjunction elimination tells us that if we have a disjunction, in this case we do, it's R or R, and we know that the first disjunct implies something, and we know that the second disjunct implies that very same thing, then we can assert that thing, right? So what do we really want to show? Well, we want to show if R, then R, right? And then we want to show, again, if R, then R. But we actually just showed that, so we don't need to show it again. So what are we going to do here? What we're going to do is we're going to hypothesize the first disjunct, which is R. Now, having hypothesized the first disjunct, which is R, what are we trying to do? Well, we're actually trying to derive R. Okay, so what does this look like? It's very weird, but just hang with me. Since we've hypothesized R, we already have R. So we can actually assert if R, then R by lines 2 through 2. Now that's very strange, but it's perfectly in accord with the rules. So again, this is logic just behaving oddly, but perfectly consistently. So this tells us that if we hypothesize R, then we have R. So if R, then R by 2 through 2 conditional introduction. Okay, so we discharge our R, all right, like that. And so now we know that if R, then R. Okay, now we did this on the first R, right? But the rule of disjunction elimination requires us to have 2 conditionals. One showing if R, then R, right, the first R, and one showing if R, then R for the second one. Now, if you, on your own, went ahead and hypothesized R again and derived if R, then R again, that's okay. That actually works, and it shows you understand the rule perfectly well. But the truth is that you don't need to do it again. You've already got it, so you can just cite the line twice. So we're actually within one line of finishing this proof. We can now simply assert that R. And why can we do that? Well, we just cite, this is by the rule of disjunction elimination. The rule of disjunction elimination tells us that if we have a disjunction, we do R or R, and the first disjunct implies something, and that is the case. We've just shown that it implies R. And the second disjunct implies something, well, that is the case, it implies the very same thing, R, then we can assert the thing that is implied, which is R, okay? So I know this sounds very confusing because we're saying R all the time, so you should stop and back it up and play it again until this starts to make sense. But here we have the very clear application of the rule of disjunction elimination. We just cite the original disjunction, and then we cite the two conditionals we need, right? That both imply the same thing, and it just turns out the two conditionals we need are exactly the same conditional, so we simply cite 3 2 times. Now, like I said, if you had derived what we have here on 2, 3 twice, then you wouldn't be citing line 3 twice, you'd be citing line 3, and then you would be citing if R then R on a subsequent line. But either way is perfectly fine. So there's many important lessons that come from this weird little proof. The first and most important lesson is that when we have a disjunction as an assumption, we're very often going to be using disjunction elimination, and we're going to be using it by proving the conditionals that we actually need. So in the previous homework, they were just sitting there for you to use, but now you will often use conditional introduction to derive those conditions. The second important lesson is that you don't want to operate on the basis of preconceptions about what you're permitted to do. You want to make sure that you explore all the logical possibilities. So it's perfectly okay to go from one line to that very same line as part of a justification of conditional introduction. It's perfectly okay to cite the same line twice in a justification requiring 2 lines, or in this case, 2 or more lines. Okay, so hopefully by now you're starting to get the hang of this a little bit, and if some of these problems were problems you struggled with initially, I would strongly encourage you now to try them on your own first before watching us do them here. Either way, always stop and make sure you can redo them without watching the video. Okay, this one we're given 2 assumptions, P or T and P if and only if T, and we are being told to demonstrate that P and T. Now, if you'll remember earlier in the previous homework, I told you that anytime you have a conjunction, there's a good chance that what you want to do is prove the conjuncts independently and then put them together at the end using conjunction introduction. Now that's a trustworthy sort of rule of thumb, but in this case it's going to make things a little bit longer if you do it that way. So what you really want to do is notice that you have a disjunction in the assumption, and what this means is that you are probably going to use disjunction elimination, and what that means is that you are probably going to want to show if P, then P and T, right? And then if T, then P and T, right? So it can be quite helpful to sort of write this off to remind yourself, not part of the proof itself, but just as a little hashtag reminder, right? So show for disjunction elimination if P then P and T, and also if T then P and T. If you can do that, you'll have your conclusion by disjunction elimination. So if you look at this, you'll see that you're going to be exploiting this biconditional. You're going to want to take it apart through biconditional elimination. You could do this now, or you can do this later. Like I said, the advantage of doing it now is that sometimes you're going to need to go back to these and use them multiple times, and so it's nice to have them freed up rather than locked behind a discharged assumption. But for this one, let's go ahead and proceed on the absence of that kind of foresight. So if we just get down to proving the first conditional, we're going to hypothesize P, right? And then you'll use biconditional elimination on 2 to get if P then T. And then of course you can generate T by P and if P then T. And then you can put P and T together by conjunction introduction. And so now you've shown if P, then if P and T. Discharge your hypothesis. And you've got if P, then P and T by 3 through 6 conditional introduction. Okay, so you've got your first you've completed the first leg of your project, and now you just have to do it again. And it's going to look exactly the same, except now you're going to hypothesize T. So the rest of this proof just looks like this. So 8 through 12 is just the if T, then P and T version of the previous set of inferences. And now you've got your two conditionals, the conditionals that you need in order to use disjunction elimination. So your last step is just to assert P and T. Why can you do that? Because, well, you have this disjunction, P or T, and you have two conditionals, both of which show that each of the disjunctions, each of the disjuncts imply the same thing, namely P and T. So one, the original disjunction, which you should always cite first, 7 and 12. All right, and so the continuing lesson for this particular problem is you should never overlook, and in fact, you should cultivate in yourself an absolute eagerness to use disjunction elimination whenever possible. Because it's a slightly more complicated rule, it's going to be rather natural for you to hope that you can avoid using it, but that is not going to work. You want to hope that you can use it. You want to hope that you can get better and better at using it. So look for those opportunities and don't shrink from them, because most of the time there is no other alternative. And it's fun. Okay, number 5 just ratchets things up a tiny bit more. Again, you should try to do this if you haven't succeeded, because what we said before should definitely provide you the tools and the insight you need to do it. So here you have two conditional assumptions, if P then Q and if R then S. You're trying to prove a conditional, which tells you that you almost automatically that you want to hypothesize the antecedent, and you'll notice that the antecedent is a disjunction. Okay, so even though there's no disjunctions in the original assumption, the fact that you hypothesize a disjunction is going to tell you that you are probably again going to be involved in disjunction elimination. Hypothesize P or R, and then your project now becomes to show if P, then QRS, and if R, then QRS for the purpose of disjunction elimination. So your next hypothesis, right, is going to be P. So again, you're going to be involved in nested hypotheses. You've hypothesized P or R, then you're going to hypothesize P in order to get QRS. And that goes through quite simply. You get Q by conditional elimination on 1 and 4, and then you use disjunction introduction to get your QRS. So now you've shown your first disjunct, if P then QRS, and again, you're just going to iterate this process, but now using R. Right, so we assert if P then Q or S by 4 through 6 conditional introduction, discharging the first hypothesis, but notice that we're still indented 1 because of the original indentation of P or R. Ultimately, we're going to have to discharge that one too, but not now. Okay, so now you're just going to prove if R then Q or S, so you're going to hypothesize R and just do the same thing. Okay, so exactly the same process yields if R then Q or S, discharge your R hypothesis, and now you note that you finished your project. As described on the side, you've got both of your conditionals, and so now you're in a position to assert Q or S. Now, of course, you're still indented, right? But you're going to assert Q or S by disjunction elimination. So how do you do that? The original disjunction, which is on line 3, the two conditionals, which you derived, 7, 11, disjunction elimination. And now, what's your final step? Stop, don't let me give you this if you don't know, you can figure it out. So if you said assert the conclusion, you are right, right? We simply say if P or R, then Q or S by 3 through 12, and discharge our original hypothesis P or R, right? So we've shown if P or R, then Q or S. Okay, number 6 gives you two assumptions, if P or Q, then S and M, and Q or P, and you're being asked to demonstrate M and S. So one of the points of this proof is to teach you something very important, and that is to resist treating formulas that you know to mean the same thing as if they are the same thing. So when we're doing proof, we are not trading in meaning at all. This is just a purely mechanical procedure that computers can do. And computers don't know what anything means. So a computer doesn't know that Q or P means the same thing as P or Q. From a computer's point of view, these are just completely different propositions. And because of that, the computer would never make the mistake of saying, well, Q or P just is P or Q, so I can get S and M in one step. So what you need to do if you want to get S and M, and of course you do want S and M, because if you can get S and M, then you can have M and S simply by applying conjunction elimination and conjunction introduction sequentially. So if you're going to get P or Q, you're going to have to prove it, okay? So how are you going to prove if P or Q? That's the question you're dealing with. Well, how about by showing it from Q or P? In other words, show #show if Q, then P or Q, and then also show if P, then P or Q, right? So if you can show if Q, then P or Q, and you can show if P, then P or Q, then you will have demonstrated P or Q by, again, disjunction elimination. And then you'll have P or Q, which you can feed into, right, this conditional, get your S and M, and then rearrange it to get M and S. Okay? So you should be able to do this proof now, having been told that. Please do it before you watch the quick demonstration of it. Okay, so begin by trying to show if Q, then P or Q by hypothesizing Q. Then it's suddenly very simple. Simply get P or Q by 3 and disjunction introduction, which means you've shown if Q, then P or Q, right? So we discharge our hypothesis and assert if Q then P or Q, and then we just do it again, just as before. Okay, so exactly the same process, but now it was for if P then P or Q. Now you have both conditionals, so you get to assert P or Q by disjunction elimination, and that allows you to get M and S, S and M by conditional elimination on 1, 9. And now it's just a matter of taking these apart and putting them back together, which is just a little bit of tedium, but very easy. Okay, so 2 important lessons from this. One is that very often when you're doing a proof, what you need to do is use conditional introduction in order to prove something that you need in order to prove something else, okay? And then secondly, don't make the mistake of thinking that formulas that you know to mean the same thing actually are the same thing. The only time a formula is the same as another formula is if it is absolutely identical to it. Okay, and this last one is funny looking, but it's actually pretty simple compared to some of the ones that you've done before. So again, if you had trouble with it, you should now be in a good position to do it, and you should do it. But the basic idea is you've got a disjunction. From this disjunction, you're going to need to use disjunction elimination. So you've got 2 conditionals to prove. And one is going to be if R, then everything over here, right? And the other will be if not R, then everything over here, okay? And that's easy because it just involves successive applications of disjunction introduction. It's worth pointing out, if you haven't had this insight on your own, is that if something follows from R, and if something follows from a formula, and it follows from the denial of that formula as well, then it has to be a theorem. You understand why? Because there are really only 2 possible states of the world, at least in the digital realm of propositional logic. One where R is true, and one where R is not true, okay? So if something follows from both R and not R, then it just has to always be the case. So it should be provable as a theorem. And it is provable as a theorem, but that's only because R or not R is provable as a theorem. R or not R is an instantiation of what we commonly call the law of the excluded middle, and you should be able to prove it from no assumptions. Unfortunately, we can't do it right now. We need one more rule, which we'll get next time, which is negation introduction, or what's commonly called reductio ad absurdum. Okay, but to just focus on this particular problem to finish things off, hypothesize R for the first conditional, get R or R by disjunction introduction, then get R or not R or R by disjunction introduction, and there's your first conditional. Same process, hypothesizing not R, and there's your second conditional, which again we need to discharge. Okay, so you got your 2 conditionals, you got R or not R. So you got your conclusion by 1, the original disjunction, 5 and 9, the derived conditionals. Okay, so that wraps up this homework review. Make sure you gotten to the point where you can do every one of these problems on your own without looking? If you can't, go back and look and then try again. Remember that in logic, there's no such thing as sort of getting it. You get it if you can do it.